everyone, this is Simplified Science by Sal. Today's session is about computational mechanics with a focus on punch test, which is an innovative mechanical test and give us the opportunity to investigate the mechanical behavior and also the shear strength of interface between the reinforcement and the matrix. Here is a schematic of the production method which I have followed to produce a metal matrix composite with copper open cell metal foam as the reinforcement and magnesium alloy as the matrix. Okay, here is the schematic of our test, which we are going to push the copper reinforcement to the magnesium matrix with a steel punch and record and report the force displacement diagram, and then we could calculate the shear strength of this test and this reinforcement with this formula. Okay, let's move on to the Abaqus part of our session. Okay, first of all, I'm going to import the parts that I have modeled in CAD/CAM software. I usually use SolidWorks to do this part of our simulation. Okay, let's find the folder that we are going to use. Very well, Abaqus punch test. Okay, the file type I use is usually step files. Let's import the steel punch. Okay, the next part would be magnesium matrix. Okay, and the next part is copper reinforcement. Very well. Okay, let's move to the property section. Okay, I'm gonna create a copper material with a description which is optional for you. I usually do this because I want to know about the materials that I'm using. Okay, pure copper. Let's introduce the density, which is 8.96, and also the next part is the elastic properties. Young modulus would be okay, and the Poisson ratio is 0.33. the next part is plastic properties. You can extract this data for your plastic properties from a simple tensile test of your base material. Okay, the first point is usually come with a 0 plastic strain, and also you need to apply at least 2 up to 3 points, but you can add more if you want. 0.3, 400, and 0.6. Okay, we are finished with our copper. Let's create a material for our magnesium alloy. I'm gonna give a description to myself with the alloy chemical composition, which is Mg7Al1 calcium. Okay, very nice. Okay, let's have some density, which is 1.73 E009. Let's introduce some elastic properties, which is and 0.33 for Poisson ratio. Very nice. Sorry. Let's have some plastic properties. Okay, 45, 0, 128, 0.05, and 229, and also 0.2. These plastic strains shows that we are dealing with a very brittle material, which is actually an HCP material. Because of the lattice structures and lattice types of magnesium and magnesium alloys. Okay, now we are finished with our materials. Let's create some sections. I'm gonna change this name to section CU, which is solid and homogeneous, and I'm going to use material copper. The next section would be section MG, which is also solid homogeneous, and also I'm going to use magnesium alloy. Sorry, solid homogeneous. I just have some doubts about the type and category of the material that I have selected. Okay, magnesium alloy, very nice. Let's assign our material to the parts. This is our copper reinforcement, so I'm gonna assign section CU, and for MG I'm gonna assign section MG, and for the steel punch, it doesn't matter because the type of our material, it doesn't matter anymore here, because we are going to introduce this part as a rigid body. So I'm just giving the section CU material to this part. Okay, let's move to assembly part. Let's bring our models. I'm gonna go with independent, click on OK. Okay, let's translate our matrix to the right place. I'm gonna choose this point and this point. Everything seems fine, very nice. Okay, and we need to have a reference point for this point, because we are going to use this reference point in our result extraction, which is very important. Okay, we are done in the step in the assembly module, so let's go to step module. We are going to have a dynamic explicit solver. Okay, and LGM is always on. Okay, let's have some sets because of our mass scaling part. Okay, I'm gonna go with port MG and CU. Very well. I'm gonna create a set. One is set RP for our reference point, and the other is set MGCU. Okay, for the MGCU part, we select our matrix and the reinforcement to use this set for our mass scaling, and I'm going to replace everything and create my set RP to extract the results from this reference point. Very nice. Okay, let's back to our step manager, create a dynamic explicit. Okay, mass scaling, I'm going to use mass scaling, and I'm going to use set MGCU sorry, and I'm going to have a 1 million and okay, very nice. Okay, now we have created our steps, but now I'm gonna have an history output. I'm gonna create an history output and name it results, and I'm gonna choose the set reference point, and I'm asking to extract the U2 data, which is my displacement, and the reaction force, which are going to be my force for my force displacement graph. Very nice. Okay, everything is set. Let's move to interaction part. Firstly, we are going to introduce our punching stop as a rigid body with our reference point as the reference point. Very good. Okay, the next constraint that we are going to create is creating a coupling between the outer surface of our reinforcement and the inner surface of our magnesium matrix. So first I'm gonna replace CU. Let's zoom to avoid any mistake. Okay, I'm gonna create a tie. I think I have wrongly set coupling. I'm gonna apply a tie, sorry. Okay, choosing surfaces, and I'm gonna choose these two surfaces by holding the shift button and the left click of my mouse. Okay, it's going to be our master surface, and I'm going to replace everything with MG to choose my slave surface, which I'm using shift button and the left mouse click. Okay, everything is set, and now you can see that we have a very nice tie, because in this kind of simulation and computational mechanic analysis, the results and the mechanical behavior of the interface is shaped by the mechanical behavior of both magnesium matrix and copper reinforcement. Okay, let's create our contacts. I'm gonna go with the general contact, and I'm choosing all with self, because in some cases during this simulation we may see deformation, and these deformations could cause to self contact, so we should make this to consideration. Okay, creating interaction property. I'm gonna go with the default setting, and everything is set here. Okay, let's move to the load part. We are going to firstly make these boundaries in caster, because we don't want any movement from the bottom of the magnesium matrix. Okay, so we are going to make these boundaries in caster. Very well. Actually, now we are going to create our displacement rotation type boundary condition for our RP, and we are going to make everything 0 except our U2, which is going to be -5. And because we are doing a dynamic explicit, we need an amplitude with a tabular type, which is 0, 0, and 1, 0.1. Sorry. Okay, everything is set here, if I'm not mistaken, and now we can go to the mesh part. I'm gonna change the mesh type to tetrahedron. Let's choose the global seeds, I think 0.5. Let's see, it's a very good and coarse mesh. Okay, let's apply the mesh. It could take times. A very good mesh applied to our parts. Everything is fine. Let's move to the job part, creating a job. Very nice. Okay, now we could wait for the result. Okay, let's see the results. Firstly, I'm gonna change the visible edge to my feature edge. Okay, very nice. Let's see what's happened to our test. As you can see, we have the most stress concentration at our interface and inside the reinforcement. Okay, let's see what happens more. Very nice and a smooth mechanical test, and you can see everything seems normal and everything seems natural. I hope you enjoy knowing about this test. This is a very innovative test, and I hope you try it. Ask for any questions, you can contact me on YouTube and my Gmail, and you can also ask for the CAE file or the ODB analysis data. Very well, goodbye, see you.